Hello, my name is Siamak Paulson, and this is the first episode of our Videocast series. We are providing this as part of the Tellings News Alert activities we're doing with our partners. A very quick introduction, and then I'll go through the presentation that we want to have from Eric Blond today. So the Videocast series, episode 1, 22nd of August 2024. This is as part of the Tellings News activities we do with our partners. And Tellings News is a newsletter. You receive this newsletter every week on a Friday, normally midday Australian time. And finally, these are my contact details. So if you have any questions about the presentation today or about the Tellings News alerts, the email newsletter that you receive, please don't hesitate to contact me. All right, Eric, we go straight into your presentation here. If you want to share your screen and start the presentation, please.
So you should see my screen now?
Yes.
Okay, perfect. So thank you, Siamak, for the opportunity. And hello, everybody. This is the title of my presentation and my contact information. So I've done this work. Okay, voilà. I've done this work on the Bituminous Geomembrane seams because we realized at some point that there is a fundamental difference between the seaming, the assembly of Bituminous Geomembrane, and between what we do for polyethylene, PVC, and other thermoplastic materials. When we do the welding of thermoplastic geomembrane, what we are trying to do is to create a continuous structure. So from one side to the other of the panels, which are joined together, we make sure that the material is as uniform as possible. So there is as less differences from one side or the other, so all the properties are constant. However, when we do a bituminous geomembrane theme, when we assemble together two panels of bituminous geomembrane, what we're doing is more a sealing. We are assembling the things together, the panels together, to create a continuous and watertight plane. So the next question is, what's happening when it's exposed to some stress, some field stress? So again, the bituminous geomembrane, when two panels are assembled together, you have here the upper panel with the polyester nonwoven, which carries most of the stress, along with the glass fiber fleece, which is the structure, reinforcement structure of the material. And on the lower panel, you have the same components plus the polyester film, which is installed in the bottom. And what connects the panel together is the bitumen. So when there is a tensile force, what's happening? You have the force on the upper panel, the force on the lower panel, and what's connecting the two panels together is the bitumen. Therefore, the seam strength depends on the properties of the bitumen. That's really the key component. Now, what's happening there? So if we think of the classical theory that defines viscosity, the equation that defines viscosity is a shear stress, which is equal to the viscosity multiplied by the distance between the planes. So here, in that case, it would be the upper sheet reinforcement versus the lower sheet reinforcement. And it's connected to the strain rate. Voilà. So there is a relation between the stress and the strain rate, which is defined with a constant, which is the viscosity. That's really the most important part. And indeed, in the Shell Bitumen Handbook, what we see is that there is a continuous relation, semi-logarithmic relation between the viscosity of the bitumen and the temperature. So what does this really tells us? It is that this relation depends on the viscosity. It depends on the formulation of the bitumen. You can see here that you have different curves. So for some formulation, you can add some additives in the bitumen to alter a little bit this semi-logarithmic relation. But for the most simple bitumen, this relation is linear in a semi-logarithmic scale, which means, to go back to the previous equation, that there is a relation between the rate of displacement between the two panels, and the temperature and the stress. So that's something which is all got together. So therefore, the seams should behave just the same with a relation between the velocity of the displacement of the panel, the stress, and the temperature. So
a very interesting concept that's Eric. If I may just ask a quick question, because I think most of our audience also want to know if this concept has been also validated by some sort of laboratory or experimental testing.
Yes, indeed. So we did some tests to validate this relation between the bitumen geomembrane seam performance and the viscosity of the bitumen. And we want also to assess how this may impact the performance of a structure made with a bituminous geomembrane sealed. So this is an example of, I'm going to save you the noise. This is an example of two bituminous geomembrane panels which are welded together, which are seamed together. So you can see here the heat which is applied. We can see the weight which is applied to make sure that there is some pressure connecting together the two panels, making sure there is no bubble, no holes in the middle, and they're all pressed together. And so that's the sample we had prepared. What you see here on the screen is a video that was made of the samples we have used after in the lab. We used the edge of the roll, so the two edges of the roll, we did not cut, so that reflects the situation prevailing typically on site. The welding conditions were ideal, which means we had a dry and smooth concrete substrate. We did not have any gravel peeking here and there that could influence the behavior. So very good control of the pressure, control of the width of the panel. We made sure it was exactly 200 millimeters. The tests were done at room temperature in ideal condition with no solar exposure, and the installer was experienced. So he had done many square meters of installation of this product. So what did we observe? First, tensile strength. We want to make sure that if we're analyzing the seam, we are not in fact observing a reduction of the strength of the product. So we did the tensile test, tensile strength of the geomembrane at different temperature. And we observed this curve. So you can see in the bottom the temperature and vertically the tensile strength of the sheet. What we observed is that we had about 25% loss at 40 Celsius compared to the properties at 23 Celsius. About half of the strength was lost at 60 Celsius, and a bit more, 55%, was lost at 80 Celsius. So this is typical of pretty much what we could have expected because of the non-woven reinforcement. So that reflects the behavior of the non-woven reinforcement. And so we want to make sure that when we are measuring the properties of the material, we are making sure to exclude that because that's not what we're measuring. So we did, after that, we did the test with a bituminous geomembrane seam only. And what we observed here is reduction that we have compared to the sheet strength at that temperature, not the initial strength at that time. And we still observed a reduction of strength by about 30% at 40 Celsius, so 30% additional reduction of strength, 72% at 60 Celsius, and over 90% reduction at 80 Celsius. So that was really a very steep reduction of strength. If we compare to the initial value of the sheet strength, it's about 50% lost at 40 Celsius, about 85% lost at 60 Celsius, and 96%. We had only 4% residual at 80 Celsius. So clearly, the seam offers much less resistance than the sheet when it's exposed to a high temperature. If we represent this in a semi-logarithmic scale, so remember that I want to go into demonstrating that the bitumen behavior is actually reflected in the seam behavior. So we know that there is a linear relation per the Shell Bitumen Handbook between the temperature, the log of the viscosity, and the temperature. So we want to replicate that. So we have a linear relation for temperature here and a logarithmic relation for the tensile strength. And indeed, we do observe a fantastic correlation for these properties. You can see 0.99%. It's almost perfect correlation. It's really a semi-logarithmic regression. So clearly the relation is exponential, is logarithmic, and that indeed reflects what we were observing for the shell bitumen handbook. So what we can conclude from these laboratory tests is that the properties of the bitumen do control the behavior of the seam, that's no question, and that the classical equation which defines the viscosity controls the shear resistance of the seam. So that was really a key takeaway from this first series of tests.
Okay, perfect. So the testing that you just showed the results, Eric, I guess most of them were done in a constant rate, as depicted on the graphs. Do you see this happening in the field as well, or what, or how relevant that would be to the
Indeed.
field condition?
So in the laboratory, we want to have repeatable values. We want to make sure that a value we're measuring on one day is going to be measured exactly the same exact value will be repeated 6 months later, 1 year later, etc. But in the field, this is not happening like that. In the field, a strain rate is rarely imposed. It's rare that the Earth is going to move at a constant rate over a long period of time. What is much more likely is that there's going to be some settlement, something happening, and you're going to have a force deformation. The force deformation will create some tension in the plane, and therefore we're going to have a constant stress taking place. Stress which can be a pressure, which can be anything. So what we wanted to validate as well, now that we know with the tensile stress that we have a relation between the viscous behavior and the temperature and the strength of the seam, we want to see if a constant stress will also create a failure just the same, will also control the behavior, create a viscous behavior. This can be answered by conducting tests with a constant load, which is in fact creep test. How do we do that? We did apply a constant load in the control environment with a temperature control, and we observed the rate of displacement. So we use the same equation for the viscosity, but we're in fact measuring in the lab the rate of displacement with a constant stress instead of measuring the stress with a constant rate of displacement. And that will reflect exactly what's happening in the field. So the test parameter, very important, because we had to conduct a lot of tests to be able to observe something that would be meaningful. We had 5 different temperatures. We ran the test at 5 different temperatures, and we applied stress at which were anything between 10 and 50% of the seam strength at the test temperature. So you can see here the seam strength in blue that we have measured on a short-term tensile test, the sheet strength in orange, and all the green dots here are the tests we have conducted. So we, at 40 Celsius, for example, we conducted some tests at 10% of the seam strength, up to 50% of the seam strength, etc., etc. So that's what we have done. And what did we measure? We did measure the rate of displacement, so the displacement between the two sides of the seam versus time, and the failure time, because eventually we did measure some failure. So for this particular test here, the test conditions were 40 Celsius, 30% of the initial strength applied. So just to explain this 30%, we have a force of the sheet at 23 sheet strength at 23 Celsius, which is 21.9. The sheet strength at 40 Celsius is 16.7. The seam, so not just sheet now, the seam strength at 40 Celsius is 11.3 kilonewton per meter. And we applied 30% of this value. So in fact, we have applied 3.37 kilonewton per meter versus almost 22 kilonewton per meter force for the sheet strength at room temperature, and that is our 30%. So for this particular test condition, we have observed a displacement rate of the seam of 58 millimeters per hour, and a failure time of for the 200 millimeter panel of 1.05 hours. So what we did, we've plotted all the numbers that we got for the different test conditions I've explained, so anything between 10 and 50% with a various temperature. And we got this series of lines that show that there is clearly a relation between the rate of displacement, the temperature, temperature meaning viscosity, and the stress applied, which confirms definitely the viscous behavior. So that was basically confirming that the equation controls indeed the behavior of the seams down to 23 Celsius. We did the same for the creep failure time, and you can see here creep failure time for the different tests. So what you see on the screen is all the tests. For every single of the tests we've conducted, we have observed a failure, including the applying only 10% of the stress at the test temperature. At 40 Celsius, we did observe a failure time. Second very important aspect, failure time were short. When I mean short, I mean less than 1 day for the worst case scenario, for the best case scenario, I should say. And if we use the trends that were observed with all these network of curve here, we can observe that even with the stress applied as little as 10% of the short-term strength of the seam, the seam is likely to fail after just a few days at room temperature. So that was really something we were not able to absolutely confirm experimentally this specific point, but it was an observation without a doubt. We did not observe it directly. However, we were very lucky that Kerry Rowe from Queen's University, in fact, conducted a very similar research parallel to us, and we did not know they were working on this, and they did not know I was working on that. And they published their results in the Geosynthetic International in May this year, just a couple months ago. And that's one of the graphs that I've extracted from their work. And so you can see here the failure time of the seam versus the constant tensile load they have applied. So if we focus on the 10% here, we can see that the failure time is going to be within days. The TR is the thickness reduction, if I'm correct. So you can see that the failure time, in fact, are going to be quite consistent with what we have measured. So it was really interesting to see that the work done at Queen's University was basically landing on the same exact conclusion in terms of value, in terms of numbers, than the work I've done going through the high temperature behavior. But it was really the very nice observation. So that was really the most of the work we've done in the laboratory, where we were able to demonstrate that the viscosity and therefore the temperature will control the behavior and of the bituminous geomembrane.
Yeah, that's very interesting, Eric. And I just wanted to ask, potentially, you know, the condition or geotechnical condition that you think will kind of create this in the field.
And that is a very important aspect, and that's where everything is happening. So there are a few conditions which can create these problems. The first one, I've put 3 here, but I'm sure there are more. In fact, speaking of Kerry Rowe, he has published a second paper where he continues, and he has even more scenarios that may reflect these situations. So the 3 that I have identified in this work were the one that you see on the screen. First, you have, let's say, waste, tailing, whatever, which are capped by a geomembrane. There is some settlement which is likely to happen. When it's waste, usually there's going to be either water drained away or whatever activity, and there's going to be some settlement. Settlement means change of dimension, means reorganization of the structure of the liner, and is going to be a contraction in some location, but the contraction will lead to displacement. And so at the end of the day, it will create some shear and peel stress on the seams. Second situation is to have a very long slope. If you have a very long slope exposed at high temperature, you will observe some displacement because, again, it's a viscous product. If the slope is exposed to the sun, an exposed geomembrane, the temperature may go up to very high numbers, and you will have some creep displacement, etc. In fact, one thing which is very interesting that I realized also researching for this project is in Canada, you cannot apply a bituminous geomembrane on a roof if the slope of the roof is steeper than 4:1. So if you project that for geotechnical work, a slope of 4:1 would be theoretically okay if we exclude everything else. But if you have a 3:1 or a 2:1 slope in a geotechnical work, the behavior would not be, the building code of Canada would not recommend to use this type of product. So that's one of the table on the range of applications. That's for roof. It's not geotechnical what they're saying, but still it gives an interesting indication, which is pragmatic based on experience. So that's the second scenario. Third scenario is a settlement under weight of structure. So here you have a quantity of waste installed on the geomembrane, and obviously because of the weight of the overburden, you will have some displacement, some settlement that will increase the length of the liner, and therefore will create some stress more or less everywhere. So that's really the three scenarios, and I know that there are more. And again, I will refer you to the work of Cairo, which is being published these days, which gives even more scenarios. So anyway, I think I want to conclude because we've been online for some time. What are the key takeaway from this work? First, the short-term seam strength of bituminous geomembrane is highly sensitive to temperature. That's something which was very clear with failure times under creep of sometimes minutes, sometimes hours, and never more than 1 day. So that's what I call highly sensitive. Second aspect, we made a clear demonstration using the two different approaches that the bituminous geomembrane exhibits a viscous behavior in the range of temperature that we have tested. So again, we've measured the stress with a constant displacement as well as the displacement with a constant stress. So it's really validated in both directions. Third, if a seam is exposed to a constant stress, and that's a very important aspect. In the range of temperature that we have tested, if the seam is exposed to a constant stress, the time to failure will depend on the temperature and on the stress. But the failure will always come unless the stress is released. But if the stress is maintained, there will always be a failure. So what is the impact on the design of containment structures? The impact, the major aspect to consider is the reliability of the seam depends on the risk of developing stress. And more specifically, I want to make another reminder about the roofing industry. Bituminous geomembrane membranes have a long history of success when used in buildings. And when I mean buildings, I mean both for foundation waterproofing vertically on concrete walls with a backfill, or on roof, or on flat roof, not roof, flat roof. And what is common to both these structures is that the substrate is not prone to significant movement. It's a flat, solid substrate on which the membrane is applied, and it will not go anywhere. It's not moving anywhere. The membrane is there to protect against water ingress. It's not there to to bridge anything. This said, when the substrate is likely to settle, when there is in-plane strain that may develop, in-plane stress will develop, and we have demonstrated in this study that this scenario could be extremely challenging for bituminous geomembrane seams and could therefore affect the reliability of the containment structure. So this is really a question of risk management. Are the seams likely to be exposed to stress and displacement or not? And that's something which lands into the engineering. So just to conclude this takeaway, one thing that I've identified for nerds like me that we should work on is the terminology. I think a lot of people are speaking of welding for bituminous geomembrane. I think we should not speak of welding. Welding has a very specific background. It's used for welding metals. It's used in many contexts, and it's not what we're seeing for bituminous geomembrane. What we are doing with the bituminous geomembrane is we are sealing. So sealing should be a better term to describe what we're doing for bituminous geomembrane. So that's really the information that I wanted to present to you today. And I hope it's to your satisfaction. And I'm available. You have my contact information here if you have any question.
Perfect. Thanks very much, Eric. I would just add one thing at the end that we're basically talking about designing with geosynthetics for applications in mining. Mostly, most of our audience in this episode are mining experts. So the main thing is that the designers need to consider, the different behavior or parameters or static or basically characteristics of the product they use in the design. So that's very valuable point from you, Eric. Thanks again for your time, and we hope to see everyone in our next episode. Thank you.
My pleasure. Thank you for the invitation.